But actually, this is one of I'm actually super enthusiastic about this technology. This came, so Matt and I were actually neighboring booths at Chemex, or 3 years ago, two and a half, 3 years ago in Boston at a trade show for composites. And like, it's like, hey, we used to talk to you guys at some point. And he was like, yeah, you know what? So we talked to Moldflow, but they didn't want to work with us. I was like, oh, let me actually, I was actually part of the conversation. We had never met in person at the time, but when we talked, we were not ready for you yet. And, we actually now, in the meantime, have developed our cool FEM, and now we can actually start talking about really cool things inside, in terms of heat and cool technology that we can put in the mold. So we should talk. So he put us in touch with his CTO, and the relationship took off from there. So Matt, in the meantime, is the CEO of Roctool, yeah, we're co-presenting today. This year we have worked on, well, the last year and a half, we worked really hard together on getting induction heating into Moldflow, and like, we're going to be talking a little bit more about what you can do with it and how it works compares to reality so far. So, cool.
Here we are. Oh, yeah, much better. Thank you. So, so going back to this, what if we are able to change that temperature, but with no hassle? Not having to preheat a lot of fluids and going through pressure through pipes. What if we find a way to heat just enough metal right before the injection so that at the end of that cycle, we can already cool down and get back to our demolding temperature? So we looked early on at resistive heating techniques, using the conductivity of carbon fiber or directly of the metal itself. But we found that induction is unbelievable fast. It's a way to concentrate enough energy in a very small amount of mass, drive that energy where you want and how you need it for your process. Because actually, we don't really care the whole tool is heating. We just want that small fragment of steel on the surface, like a flash heating, right before injection. And as soon as you're done injecting, then you can drop your temperature. That's the key. So we have what we call a high-speed heating technique. We have channels inside the molds. In those channels, there's copper braids, which we call coils or inductors. We spent quite some time to design them, to find the right combination of copper braids and insulators. And then we have a program, an interface, connecting to a power unit that is directly interfaced with the press machine. So we run in a fully automatic mode. For those who came to the last plastic show at the NPE, we were running with cross Maffei or angle constantly during the show, non-stop in an automatic mode. We didn't have one guy that was like dwelling the frequency of induction. It's fully integrated, so it doesn't feel actually there's anything going on. It's actually a headache for the marketing people to try to make it look cool, but we come up with some cool stuff. So if we take a closer look what happens inside the mold, the idea again is to drive a magnetic field within the channel, and that magnetic field, when it's very well driven, very well calculated, we know exactly what's going to happen, how fast we're going to heat the surface, how well we're going to heat the surface, and what it will take to cool it down. And that is very important, and that is why we're spending time with Autodesk. Because if we can control this before making a mold, we have a very clear image of what happens in the tool before making the mold, before any serious investments. It's not an empirical approach where we make a tool to find out if we can make a good part. No, we design an induction network that is relevant, that is proven, and then we work on the tool design with the tool maker. So we do not heat with the magnetic field the surface of the tool. We heat the inner portion of the channel, and then by conduction, we will heat to the surface. So, I don't know, I think in the last 15 years, I used to go a lot to Japan in the early 2000s. That's when really everything started. When multiple companies had the steam technologies that was rising at that time. Then I spent some time in Korea with tool makers about electrical heaters and rods and resistance. And also in Germany with pressurized water. But there's one thing about induction that comes out, is the efficiency, the control, and how we can predict before making a tool. So this is a quick chart to demonstrate how much faster we are versus other full processes and other technique, and also how consistent it is from one cycle to the other. Again, remember, when you're at home, for those who have induction, you can boil water very, very quickly. Then you remove the pan, you turn it off, and you can put your hand right away on the stove. If you have an electrical resistance, you can't touch that right away, get away a little. Same thing if you have water circulating in a pipe, you can't touch that pipe right away because there's a lot of heat transfer, a lot of conduction going on. But we don't want that whole tool to be heated. We just want that little fragment flash heating so that when the resin comes in the tool, finds itself very comfortable, under control. So this chart is just a quick idea if we do a benchmark. The other very important thing is, and I think that is why I hope Autodesk picked Roctool, is there's no temperature limitation. So the resin providers right now are very aggressive in building, let's say, new recipes that cover so many different applications. Even applications that used to be painted and now they're not. Sometime we will have maybe a scratch-resistant resin. And maybe that scratch-resistant resin will be 250C in the tool to get to the ultimate surface quality. Well, you don't want to be limited in temperature. If you do investments in your shops as an injection molder, here you know you'll be able to push that temperature all the way to peak PEC and any temperature. Right now we're doing Tixo molding with magnesium to very high heat. So that's the good part about induction. There's no temperature limitation. That may be the most important slide before Hanno. Clearly, he has the good stuff. But the last 5 years, we've been busy. All our engineers and doctors and all the people at Roctool that make it happen, instead of spending time on the tools themselves, we spend time on the tools to make the molds. How can we predict the heating? All the way from the heating pattern and the cooling pattern. How do we design a tool that becomes very, very fast? Because out there, a 5 seconds penalty for some companies is a very big deal. So how can we heat the mold when the press is open? As we demold parts, already we're done with the heating for the next cycle. So all of this is done with those 3 steps where we can simulate the magnetic field based on a design. So let's say you come up with a door panel for the automotive, a coffee machine, or a smartphone. We can have a quick look at what's going on. Then we apply a thermal analysis. Based on those results, we find out what's the heating pattern. Is there a hot spot, or, oh, it's not heated enough here? And we position our inductors the right way. And when we're done with that, we have a very secured image of what's going to happen in the reality. And it correlates. When I was talking to a gentleman, I had no clue he was there for that trial. That was kind of funny, but what we do is when we start a molding trial, we take a lot of thermocouples, manual thermocouples, and we make sure it relates to the simulation we did 2 months ago before the mold existed. That is the first work we do on any plants. And more we're getting to 90, 95% in terms of heating quality, and it also correlates with the simulation results. The equipment layout is pretty straightforward. I would say in gray, that's what you typically have in an injection facility, and in red, that's what we add. So the generator, the interface, which is a remote control connected to the generator, and there's a small capacitor box on the bed plate of the press machine, and then a cooling unit for the generator, make sure that the power unit gets cooled down. The rest is standard. We do not ask for any radical change. It's more of an add-on to the existing setup. Those are equipments. We design our own equipments because we want to make sure we get the best for our customers. They range from 50 kilowatts, 300 kilowatts. Now we released the double zone generators, which is very interesting for those who have challenges in warpage. We're able to control the heat of the core and the cavity at different temperatures and also different speed. So it's one unit with 2 heads, and this way, for some challenging parts, you're able to balance your temperature in the tool and have different temperature controlled on the core and on the cavity. It's also a way to have on large parts two network on the same cavity with not the same temperature on the same side of the tool. So it's all about design, because again, the OEM, at the end of the day, doesn't really care it's induction heating. I mean, if they like engineering, they may ask, oh, it's interesting, okay. What they want is new design, beautiful parts, light weighting, more performance, cost reduction. So that's our driver. So how do we make it happen? Well, we need to work at different levels. We need to work on the material and see really, with the high heat, how can we improve the molding for that material that has been selected by the OEM? Thickness of the part, how far can we go? And that's where this collaboration with Autodesk is going to allow us to push the limits and predict more and more challenging designs. So, beginning of 2016, we're releasing a very large campaign. We hired a few people for that. We really hope Autodesk will be part of that. We know they will be. What we call high-definition plastics. The high-definition plastics is really applying what we know every day around us. When we watch TV, now we like to watch movie in HD. When we look at our smartphone, whatever we do, high definition is becoming part of our life. However, in plastic, sometimes it's okay to see a weld line for some manufacturers. It's okay to have a sink marks. It's okay to accept those defects for years and years that we've been having. Well, we say no more. So we release high-definition plastics that will gather the best materials, the best heat-cool technique from Roctool, the best software capability, so that we have something robust that we can offer to the OEM with the ultimate plastic part. That's our ambition. And beginning of 2016, stay tuned, because we will release more and more results about our achievements. Those are the four main drivers of that HDPE. Number one is to create unique aesthetic directly from the molding without secondary operation. So unique aesthetic means unique texture, high gloss, low gloss combination, patterns, anything that create a unique part and allow the brand to differentiate itself from another brand and creating their own brand recognition. Textures and functionality. It's not only about how it looks, but it's also how it feels. If you replicate very well your tool surface with no defects, you can access a new level of functionality for your part, like a feel or a grip or other functionality that we're working on right now, like micro replication, nano replication, all the way to a hologram. It's unlimited design possibilities, because based on a 3D file or a drawing that you might have, you can apply that on your tool and then it will show on your part with more than 95% replications, versus conventional where the molding does not allow you to do this. And unfortunately then you will consider a secondary operation to cover the issues you have on the part. So let's remind ourselves about some of the old advantage that we did digest already for quite a few years, but we're past that because it's so obvious. But clearly, we get rid of weld line. Weld line is still there, it's just that we don't see it anymore. Two flow of material getting hot in a tool instead of getting in contact, they cross each other, the eye doesn't pick it anymore, they become stronger and it's better looking. So we have many projects right now that are using the technology just for that advantage. However, we think that was just the tip of the iceberg. We're now looking at more and more advantages to push the limits of plastic processing. A lot of parts, if we look at inside a car, you have trim with high gloss, low gloss, texture, metal, piano black. I mean, you know, each design team come up with their own identity about what they want to show. But if it is that each part has to be individually decorated, then cost goes up, then the designer gets frustrated because his purchasing department comes back and say, can't do that, that's too expensive. Got to find a different way of doing it. So if you control your temperature in your mold, you will replicate whatever is on your tool surface. So you can create solutions where actually it feels like it's different parts, but it's just different patterns in the tool that create this effect. If you look at this bezel right here, of a very low gloss surrounding on the air vent, the inner portion of low gloss, and then the ring of a high gloss, it looks like there's another part that was snapped on it as a ring, but it's not. It's just the whole part itself. And that differentiation of texture creates unique design solutions. The sink mark always been a challenge, and we do not say we get rid of all sink marks, because we would be a crook. In plastic processing, we know how difficult sink marks they can be. However, if you know at high heat during injection, you can hold packing, well, most of the time you'll be able to overcome or reduce. And that is nice, because there's a lot of parts that sometimes we don't make the right choice about the rib ratio. And then we end up with a part and we show that to our customers and they go, no, that doesn't fly. So if you know you have a little help at that time, the high heat molding clearly is a way to overcome some of them. It's also a flow improvement. I mean, as you understand, the temperature is key to improve injection molding. So we did a lot of work, for instance, with SABIC. We were able to demonstrate on key resins that from one gate conventionally, we had a flow improvement of 10 to 20% with the same material, same tool, just turning on the temperature. And this is very important. As you can imagine in the electronics, with those very challenging thicknesses, having this ability is a serious advantage. This is our vision about what we call the high definition, the evolution of plastic parts. We know, and we're all here because we believe in this, injection molding is #1 for design functionality. I mean, it's unbelievable. In 30 seconds, you can have a part that is ready to go that can be snapped to do something versus compression molding or others that cannot have all the back features. And so this we know it's a very strong process. It's also great for productivity. It's so quick, all the way to cosmetics, electronics, automotive. If we add the induction heat, we add those advantages that we just talked about with the top surface quality, reduction of defects or elimination of those defects, thinner wall, and also pushing the limits, reaching materials that are very viscous and very difficult to handle that now become possible. But that also opens up what we call surface-oriented resins. If we know that with the induction heat, we get rid of secondary operation, then the resin provider comes back in the game and say, well, I got to work on solution for scratch resistance, on chemical resistance, because the part is as is. There's no more cover-up. So we do a lot of work with the resin providers about color, particles, durability, chemical resistance, and also additional features like feel, cold touch. So we think this is just the beginning. And finally, last but not least, if you know that during the molding you're going to have a premium part coming out of the tool without secondary operation, you might think about using your tool surface as a way to decorate the part, and you can push it with the laser texture, creating unique designs, new aesthetics, and also patterns that could be very important as a branding method. So that's this evolution that we witnessed the last, let's say, 18 months. This is just a quick case to demonstrate the replication on the tool surface. So if you take a RAL value on your tool texture, or VDI that we use in Europe, let's say here it's a 22 value, and conventionally on that polycarbonate that is molded at about 180 F, the replication of the texture is about 17 on the part. Okay, so that gives you an idea. And then this little square here is a 19 to 24, 22 to 27. From the same tool, and just turning the induction on right before injection for about 3 seconds, we ramp up to 320 F. That replication ramps up to 21, as you remember was 22. But look, as you go to finer textures, 23, 24, 26 to 27, it's almost 100% replication of your tool surface. What happens is then visually, the part stands out. Right away, it looks very nice, very premium. But it's the same tool, same material. There was not addition here of any tricks whatsoever. It's just using the temperature. I just brought a part here that didn't bring many parts, but this one is relevant to that level of quality you can reach with the laser texturing. And I'll circulate it. So that's just, that's an ABS. Yes, ABS. I know it's hard to believe. The gate is right here in the middle, so we get rid of the blush. There's never a blush with induction because the material close to the gate stays warm. And this is just what's texture in the tool. Thank you.
Show this?
So whoever had French fries, you might want to hold the part from underneath so that the last person can see a nice part.
Can I show these?
Yeah. Those are also another example of a texture. So just to explain, there's part without. It's in French. In the back it says sans, so without. And we push the limits to include directly hologram on the tool surface. So conventionally, you almost don't pick them up. But when you turn on the induction, that turns them on. And you can see them like some kind of an image. So that's interesting for maybe some applications for protecting the application itself, making sure that it's not a copy directly from the mold itself.
And the interesting thing I find is like if you put your finger over it, you kind of can barely feel anything. It's amazing.
So the time we circulate those few samples, last but not least, and I think we have a lot of work with Autodesk to continue developing a strong tool. And I know you already spent time on the Mu cell.
Yep.
So that's great. There's potentially synergy here. But whenever you mix plastic with something else, let's say that you have a fiber reinforced resin, short fiber or long fiber, that can be glass or carbon, or a blowing agent or talc or any filler. During that process, when you conventionally mold, the resin and that filler are mixed up and they freeze right away, so they show on the surface. But if you're able to drive the temperature right before injection, the resin at all time, whatever is the resin, will be much faster, will cover that charge, and will have all that filler disappear on the surface. So that part right here is conventionally molded with the Mu cell, where with laser texture details, we have a high gloss zone, we have a big weld line in the middle, we have a little square of super thin wall, less than 1 millimeter here, and then low gloss on the top and the bottom. And you can see the mess because all that Mu cell, like little bubble of gas mixed up with the resin, get on the part, and then this is it. It would be the same thing with fiber. And then as we turn on the temperature, we bury it a little bit like a sandwich structure. And then you only have that nice PCABS on the surface that reveals all the details. So you can see here, we had almost like a holographic decoration of a sitting position. It was just a part we made for the NPE. But what's funny is that it doesn't even show like it wasn't there. So that's, I think it's a very nice example of how far you can go controlling the temperature in your tool. Thank you. So, Hanno's turn.
Yep. So we implemented the technology in the 2016 release. So we wanted to do something over here. But rather than repeating what we did at NP, which was sort of like an introduction of the technology, we took the opportunity to see if we could actually get some validation work done. So together with the Roctool and ourselves, we actually did a good validation study. And last week, it turned out we couldn't get all the data off the machine, so we actually had to switch tools. And but a bit of a rush to get the data in, but we were able to get actually pretty good results across now. So the induction heating is supported for dual domain and 3D simulation for cool FEM, and it's part of the Inside Premium and Ultimate license. And yeah, we have a pretty good product, I think. So we worked really hard on it, and we developed it from scratch and built it in a fairly short amount of time. Wait, all the way. All right. So the tool we took for the validation is like a similar cell phone type of cover. I'm not entirely sure what it is, but it's injected from two sides. We have a PC macrolon used there, and some grainy textures on the surface there. We have instrumented a couple of sensors. There's a couple of pressure sensors. Oh, sorry, pressure sensors built in, and a temperature sensor in the middle over here that we have some data from. And over here somewhere, yep, we have a thermocouple to control the Roctool switching on and off. So we're running on an angle, and we can grab some graphs from the machine as well there. The tool, I'm not going to go into too much detail, but there's a couple of components that we have to point out and model separately a little bit, and so bring it into mold flow. And I'll go through this in a bit more detail in the next slide. I'll build it up a little bit. So the first thing we need is a part, fairly obvious. The second thing we're adding is a set of induction coils. This is not the exact model that we use for the validation. This is the model we use for the MPE for the demo, but it was pretty good to illustrate in terms of which components have to be modeled. So in this case, we have two different induction coils on the top and the bottom half of the mold. We have to model an air gap around the induction coils, and the air gap, my understanding, is it helps to concentrate the heat on the surface there. So it's a pretty important component of the design. Then after we heat up the mold, we obviously have to take the heat out. So we model cooling channels behind the induction coils. Build our mold or insert around it, like you can actually build a bigger tool around it even. And I think we're set. Yeah. So in terms of the components, we just went through it, but there's actually, the modeling itself is actually, requires a bit of attention, because a lot of the heating actually happens very close to the surface of the mesh. So we need to have a good amount of definition or good amount of elements near the surface. And we actually put some effort into understanding how fine or how we can build a mesh. So the heat gets dumped on the skin, and so we have what we call the skin effect, and we have to understand that skin layer, skin size, we can calculate, and we can help that to drive our mesh size. So we can calculate the area between the insert and the coil, but the metal part needs to be skin layer. So we have to calculate the mesh size is the skin thickness divided by 0.8. That becomes sort of the overall mesh size of the mold. And the skin thickness is, I forgot how to calculate it. It's documented in the validation document that we created in 2016. I'll have to pull it up. Another important piece is that actually will drive the normal mesh thickness. But another piece that actually, when we mesh the molds, is that we actually have to increase or create a couple of extra layers very close to the skin, called enhancement layers. And by default, this is set to 3. Yeah. So as soon as you have induction coils in the mold, this set of enhancement layers becomes an option in the meshing, and the mold meshing. So, but in general, we'll see that there's actually a fair number of elements, and as you can appreciate, there will be some calculation time involved in here. Then we give the properties to the tool, and we describe the cycle, so the process settings. So we have to define properly which components are made out of copper, which are steel, and what kind of steel, because the different steels will actually have a different magnetic effect, and we actually have to key in some information about the magnetic properties of the material. Because we don't, as mold flow, we never had the need for that. So there's some information that we have to provide into the analysis to understand how the different metals respond to an electric current. To describe the process, there's so one of the things that you'll notice later on is if you animate the temperature distribution through over time in the mold at the beginning of the what we normally start of injection is already at temperature, and you actually start like seeing sometimes already a bit of a drop off in temperature. So it's not the ramping up of temperature actually starts before the shot starts. So it looks a bit odd in the analysis here and there, but it actually is correct. So we have to properly model or specify like how your induction actually happens when you start the induction before the analysis, the start of injection. Then, like I said, we have to give proper properties. The air have to be modeled. Like this is one of the occasions where we actually give properties air to the steel, to the TED mesh, and model a copper, or add a copper to it, to the induction coils. Then we specify the inlets for the induction coil, like where the conductivity goes in and when it comes out, and specify currents and frequency. So that's very important. That will basically drive the amount of heat that's being dumped on the skin. Important controls. And specify your boundary conditions for your cooling channels, and then I think you're off to the races. So yeah, what happens at that point, basically we start the induction analysis. We understand sort of what how much temperature being dumped on the surface. That goes into our cooling analysis, and we also have to extract heat, obviously, so there's some good amount of calculation involved here. It's over, we do typically the best results we get from induction heating from startup, so it will take a bit of time to get to that point. But there's a number of specific results that are related to the electromagnetic results. So the current density, joule heat, magnetic flux density, the source current density, and the source electric potential, and there's some other results on real parts and virtual parts, and it's pretty obscure. But at the end of the day, those type of things you're typically not going to use as a mold flow user. What we're probably going to be looking more for is how the temperature cycles through goes through the cycle. So what you'll see is that before the next injection start, the mold is already at high temperature. Where your part is over here, we actually bring the temperature up to temperature really quickly. So at the end of a cycle, you will see that part being very blue, and then really quickly it ramps up to the process temperature. And that's actually one of the key elements of induction heating. It's just flash heating where you need it. So, and then like you see the second like bump up and coming again. That's partially because of the plastic actually going into the mold to give the second bump in temperature real quick. We can also look at the temperature of the part surface. So we look at it still at the mold surface right now, but just at the skin layer that's touching the part. The results I'm displaying over here are actually not the exact result that I got actually 20 minutes ago or like an hour ago. I was able to get the previous animation in, and this one I just didn't have very time to finish, but it's pretty close. And obviously we can extend the whole thing to a warp, so we can actually understand, like Matt said, how the part deforms as a result of the injection molding cycle, as well as taking into account the temperature cycling. So it's a pretty flat part. We're excited about that, obviously. We can also do the same process, obviously, on a machine and actually extract a bunch of data from the machine itself and from the inductor. And this is the experimental data. And unfortunately, I have another graph coming up that you will have to look at this graph and look at the graph I'm presenting later. That's the mold flow results. But so you see, like at the start of injection over here, the mold is at temperature, and it cools down, and then really quickly ramps up to production temperature towards the end of the cycle. Be ready for the next shot, obviously. Come on. So this slide is, like I was not able to update this, but this is the result that we had on Monday, where the experimental data, and we had the calculated data. Trend-wise, really, really good. We still had a bit of a delta over here that's, we had a couple of things that we still wanted to explore. We didn't have all the information quite ready yet, so the last run ran overnight. Like I said, I got the end results 20 minutes before the presentation, so I was not able to update this graph, but I'll do that before the data gets posted. So trend-wise, we're really good, and we're seeing that if you look back at the previous slide, the max temperature is actually slightly over 150 degrees centigrade, and actually we're pretty close with that in our simulation. So there's still a number of things that we're sorting out there in terms of the inputs on this, but we're very confident we'll be able to sort it out in the next couple of weeks and actually create a really good demo case for this that we can jointly use. So the point of this presentation is like the whole high definition plastics opens up a lot of possibilities for designers to actually be really creative in how they design or how they market their products, right? So if you go into like a cell phone, like if you look at cell phones, a lot of them are just same piano black. If you give this a pattern, all of a sudden it becomes a competitive advantage. It looks cooler than the just straight piano black. Even if you make a piano black really cool, it's obviously nice, but it opens up new possibilities for people to differentiate themselves, and we want to be part of that. So obviously there's a lot of complexity involved, and like before you start like cutting steel, you want to really know how this is going to work. So this is why we're partnering up and do simulation before we build a mold, because once the thing is there, we're dealing with it. So yeah, and it helps us actually validate sort of if this is feasible technology before you start cutting steel. So before we say goodbye, I want to actually acknowledge a lot of hard work that our team members have done on our side. So like in France, Guillaume worked really hard with Stefan to put this together and get this data set ready. And on our side, we have Clinton in Australia that's been really instrumental in this work. So, any questions? Many. Good. Yep.
There's different ways of.
So the question is for people on the line. So can you use different steels to drive the temperature in the molds, right? In different ways. Yeah. Yeah. Different zones. Yeah.
We wouldn't do this because then that would create really complex tools, and thermal expansion of steel being different from one to the other, we would expose ourselves to maybe some gaps in parting lines and so on. So to address that, it's just about the distance of the induction network from one zone to the other, where actually you will have a temperature difference from one zone to the other because of the location of the induction.
Yeah, so I had a question, actually maybe for you, Hanno, with some of the simulation work that was done. So we saw a lot of the stuff being done with weld line analysis, and now with the 3D analysis in 2016, you can actually see how the weld line may move during flow. And I know that with the Roctool technology, how you can eliminate the appearance of weld lines. Is there anything that's being done to be able to predict the elimination of weld lines in the software?
Yeah. Very good question. I get that a lot, actually. We have not gotten to the point yet, but we're very interested in actually doing that. So one of the things that we've been discussing in the last couple of weeks is how we can take this partnership to the next level and do some really cool things. Because like most of it is really good in simulation, but we also have things like visualization tools like VRED that can really showcase like what a texture with, let's say, Roctool could look like. And we have to look at how we can look at visibility of weld lines, for sure.
The idea will be for a designer to look at three main categories. Number one is typical flow analysis with the induction. Number two, how good the surface quality can be. And number three, performance, weld line strength, warpage, and so on. So those three big projects we will work with Autodesk.
So I actually have three questions. Have you done any injection molding with weld lines in regards to materials that contain metallic flake? Because typically with metallic flake, weld lines are the bane of the existence. So does this technology help with that?
So yes, it does. However, I gotta tell you the truth. It's awful to mold metallics.
Yeah.
So it's a little bit of an accident on the highway. You know, all the particles get together and then it gets darker and everything. So the good answer is the following. First of all, you need to have a gating configuration that help you avoid that big accident on the highway. Number two, you need to have a very high heat so that you can drive the resin. And number three, you need to play with the injection speed. If you gather everything, then you have high chance of success. But some of those applications, because of the form factor, just don't allow you to do that. So we found very good results with acetal, POM. We also did some trials in Japan on a PCABS with metallic particles. They were kind of very thin, and we were able to have a fan gate so that we would push them in the same direction and try to avoid a little bit of those flow marks. But at the end of the day, knowing that now you can replicate your tool surface, how about just taking a nice gray ABS with no particles, so cheaper, and using the tool texture to create a metallic effect?
Okay. Next question is, you said you were doing some research with MuCell. Two parts really. Were you using counterpressure at all? And have you done anything with chemical blowing agents?
So yes. On the MuCell, we have now very nice experience. Actually, we're in production in the automotive with MuCell to create A-class components and using MuCell for the light weighting. For blowing agents, I'm not the material specialist in the company, but we tried a bunch, and every time is the same result. Recently, we noticed that at too high heat, some blowing agents do not respond the right way. So it's finding the right combination of your material and your blowing agent. And finally, we do have two projects right now with counterpressure to use that to get rid of the sink, but then use the Roctool for a good surface quality and so on. So
you're not, the counterpressure isn't to keep the foam below the surface. That's being done with the heat. You're only using counterpressure to counteract sink issues that you're seeing?
So you're asking if we're using counterpressure only for sinks?
I'm asking, are you using counterpressure for aesthetics?
For aesthetics?
Yeah.
So that's what they claim, and what I've seen, I'm not sure that without having a higher temperature, how can you get a much better surface replication and push the surface quality? So I guess it's maybe a debate, but I know that with the temperature we do that. I think the counterpressure mainly should be used for sink mark mitigation. I see that as their number one feature.
Okay. And then when you're constructing these in the tools, what's the actual distance that the coils are from the surface of the part? So
there's a little bit of a thumb rule, right? If you have about 60 millimeter diameter induction network, you're about 60 millimeter to the surface. So then 8, 10, 10.
And how large of tools have you done thus far?
We made a hood. Right now we're making a door panel complete. And very soon in the aerospace we will make a very large component.
Great, thank you very much.
Sure.
So,
you're asking if we have more success with amorphous versus crystalline materials. Actually, maybe 2 years ago, I would tell you amorphous material give us everything we need with the high heat. I mean, it loves it. Polycarbonate just feel the heat, like it's unbelievable. However, the last 2 years, year and a half, we spent a lot of time on crystalline. It's not necessarily surface quality, but it's a performance increase. It's not something you see, but it's something you can measure. Weld line strength, warpage control, and also a way to get rid of scrap and having a more consistent process.
So, going back to the multiple side of things, then do you look at the specific heat content curve, or maybe the PBT data to show where that glass transition phase is, or where the TC, the crystallization? And is that your target at TC?
Okay, so that's another big question. We could talk for an hour. So I'm just going to say for the recording, you're asking, are we going all the way to TG, TC? I mean, how far are we going per material? Remember one thing, the target, because of the companies we work with, is to find the first temperature that allow us to make a better part. So we don't get fancy. We can go to 200C, but maybe for that resin, 155 is good enough. So usually we go gradually to see the impact of temperature. Some resin, I agree with you, the very viscous resin, ultra polymers, require that we get very close to TG, very close to melt. And that's a way to unlock some of those issues they have. But for commodity resin, for consumer products, no need to get that high. Sometimes a 30C increase over conventional already gets you the quality you need, get rid of sink, and improve the part.
I had a question, maybe an easy one for you. So as the inputs for the software, you need current and frequency, right? So it sounds like you do some simulation on your side or some calculations to determine what's optimum. I imagine if you're offering this to a customer as a package almost, where you're going to say this is your frequency, this would be your current that we would recommend, and then that's how they'd run their simulation.
Okay, so at the end of the day, this product that we have with Autodesk is the beginning. It means that down the road, there will be a level of independence for the customer to really have a final induction configuration. But we have 45 engineers doing that. So this is to have a very quick understanding about how far you can go with the Roctool using MoFlow. And then when we start a project, we will fine-tune the induction configuration, the induction layout, and work with the tool makers to make sure they follow the requirements.
The examples that were shown on the induction coils, they are straight lines through the tools. Do they have to be? Can they follow the contours of the part? And then I guess I'm curious about how you actually get them in there if you've got curved or, you know, multiple paths or whatever.
That's a good question. So the question is, well, you had a microphone. I don't have to say it again. So, I mean, to answer your question, I'm going to ask another question. How do you do cooling lines today?
Well, traditionally gun drilling, and they are straight, and then, you know, we go around corners and whatnot.
And you suffer from the availability of what the toolmaker can do and everything.
Exactly.
Same thing for the induction. We have a network with channels. We've got some 2D form factor where we can just gun drill straight lines. We have a way actually to take a cavity, make an insert where we flip the cavity, drill our groove network, machine it, trap the inductors, and then put back in the cavity. This way you have a network that is following the contour of your part. Sometimes we take the block itself and machine it from the back. Sometimes we do both. We have straight lines for the surroundings of the part, and then just one section when there's a difficult contour where we machine it. So there's not a one answer. It really depends on the part. However, with tool making technologies going up, with those machines that get more and more performance oriented, we can easily integrate our induction. We have actually now induction that is equipped in moving features. So I think down the road we'll be able to have a very 3D complex shape for any tools. It's just a matter of time.
Yeah.
But
So basically your induction coils are flexible and can go around corners and whatnot.
They actually look like this wire right here.
Okay.
They don't break, there's no flow. So once they're in the tool, then they're good to go.
Very good, thanks.
Sir?
One moment.
So, So I'm a former Samsung Electronics engineer, former. So when I work in Samsung Electronics, many kind of the heat and cool technology examination, and finally choose the steam method. So I have two questions. The steam method, then your technology using that type, and mold making cost is how much different? Mold making cost.
Cost?
Mold cost.
To answer your question, I will actually give you another answer. The question is, how many tool makers are willing to make a steam mold? That's the question we need to ask ourselves first. And how many production facilities are willing to have engineers and process operators operating with water under pressure at more than 180 C in pipes going through a mold? So when we developed this technology, we looked and we browsed of other heat cool. And our number one thing was, how can we have a system that is so safe that it feels like you're buying a hot runner? And that's what we designed. Today, when I get downstairs and I see the machine running in our lab, you don't know there's a heating system that is going maybe to 400 C. You don't even feel it. It's so quick and safe that it doesn't feel like anything. So that might be our number one difference versus steam.
Thank you. And second question, when another method is just suggested people when we was choice, electrical heater type, the checking type. One of the big issue happened. That heater make a magnetic field nearby the mold area, so a lot of dust come inside the cavity. So make a surface problem. The induction heating don't make that kind of issue?
No. You see
the dust coming.
Remember one thing. If you use electrical resistance, you're having like a hot rod that heats, and then at some point the heat goes everywhere. And cycle after cycle, you're building heat. So what they do is they try to switch steel and put aluminum in the middle to kind of take away that energy. But induction is not. The 4 seconds heating, as Hanno was talking about, the electromagnetic skin death, if you heat 4 seconds every time, there's not enough time for the heat to go anywhere. It will always remain in the surface area. And at the end of the cycle, we cool down, so the water takes over. Versus the other heat cool, where it's very difficult for them to control in a consistent way, because at some point, conduction keeps going. So then you get to stop production because everything is hot.
Thank you very much.
Sure. Sir?
Thanks for the presentation. It was interesting. I just have one question. You mentioned, answering the other question, that actually you're heating up just a really small portion of the mold. Isn't it a problem during the mold's life cycle that you heat it up and cool it down really fast, and you have high temperature differences between, or in the cycle?
No, it's actually better for the tool. If you, we need to look at what we're doing today. Today you have a material that is preheated, 650 F, that you drop on a cold surface. So you have about a 580 F delta on steel. What we're doing is we ramp up that tool surface temperature 50, 80 F more. So we reduce that delta to what, 450, 480 F? So I'm asking you the question conventionally, with that very big delta that you have, do you hurt your tool? So you can use plastic to heat steel today. That's what's happening. What we do is we just higher the temperature before the resin comes in to ease. Actually, why do we have a drop of pressure requirements? Because it's easier to mold. So we have the same tool life. There's no cracks. We have about 300 molds in production today. None of them have a crack.
Another question, just curiosity, because you mentioned that this is set up to run automatically in your systems. So how do you hook in your induction controllers into the machine?
We work with top machine manufacturers and synchronize their system with our system. So there's an input and output. There's a hearting plug, 15-pin, and we take over so that the thermocouple in the tool gives the signal to the press machine when to trigger the injection. So actually on the cycle on the press machine, you can see when, let's say you program on your remote 150C, then the temperature goes up, and when 150C is hit, that turns off the induction, and you see the machine doing the injection. It's just a program. Behind you.
Are you limited to, if for parts that have low cycle time, are you limited in terms of the amount of time you need to raise the temperature before injection?
Theoretically, that's the good part about induction. It's just a calculation. Like a flow water, it's flowing, so there's a little unknown there somewhere. With induction, we can, if you want heat in 1 second, it's just about how much power do we need, how many kilowatts, looking at the surface of the part, the type of steel, like Arno said, if it's a P20, H11, H13, depending on the conductivity of that steel or thermal properties of the steel. Even we could go to some premium steel to even accelerate that heating step. So we have no limitation. But then it's a compromise to find. How fast do you want to go, but how much are you willing to pay for that tool if it's too exotic? So we try to stay with standard P20, H11 steel and tailor the best induction layout to give you that speed. But then what if I tell you that actually your demolding, when you demold, is 2 seconds, let's imagine. Well, what if we use that? What if you use that time for the next cycle so that we use that 2 seconds window to do our heating so that it doesn't damage your cycle time?
Actually, I had a question for Hanno. The simulation that you did, what type of time did it take for the various stages, both the model preparation and then the calculation for that size? Day and a half for the calculation to run through everything? Okay. And that was just on a local, that wasn't on the cloud? Or on a local machine?
But it was like from startup, so it's...
Oh.
It takes a while. Well, yeah, so actually it's a good point. So Clinton ran an analysis that took 2 days, and Guillaume in France ran the same analysis in about a day or so. So there's significant.
Great, thanks. I also had a question on the square samples that went around. Is that P20 for the cavity, or what steel did you use?
Oh, wow. On that, I think it's H11, this one, most probably. When it's highly cosmetic and high-speed cycles, best compromise of speed and quality, H11.
So when you're using high glass-filled resins and you're keeping the resin below the surface to get the better aesthetic, are you finding that you're having reduced tool wear due to glass? So you're lengthening tool life with heat?
We never, that's a good point, thanks. I'll remember that one, true. Maybe, I don't think we have any measurements at that level because we usually hard coat the tools that run with fiber. But over time, I know we have a customer using fiber. We could ask him if there was a difference versus conventional.
I did. Hold on a second. I'll get it.
There.
Obviously, you can't patent induction heating.
I can't what?
I'm just thinking about, like, you can't patent induction heating as just a theory.
You mean just
But
induction heating?
You patent it for injection molding, right?
Not only injection molding. We have about 80 patents international that comes from the tool, the induction configuration, applied to compression molding, injection, metal processing. So we didn't patent induction molding. Right. Nobody can. However, we patented it for tool configurations.
Okay. Are you currently working with any hot runner manufacturers?
No, but we're thinking about it.
Okay. Let's talk.
I remember, thank you. I haven't used the module yet myself. I was wondering if there's a database for the steel tools for all the different settings that you have to have in there, or if you need to find that information, how would a user go about that?
Yeah, I think they have a better believe that the Roctool guys have a better database for this right now, and that's something we're going to be working on too.
We do. We have
We do have a number of materials in the database now, and you know, it's part of the standard database for tool steel now. You can put in these properties if you have them available.
Yeah, but it's still certainly something that will grow.
Yeah. Have you done any sensitivity studies for that? If there's a difference in the steel tool, in the tool steel, how that's going to affect?
I'm not aware of that.
Yeah. Is that a large sensitivity there or not? I would imagine would be.
Good question. I don't think we've done the work there.
Okay.
Nobody else?
Oh, that's enough.
It's beer time? All right.
Thank you.